talk about is how do we alter the concentrations of our solutions. We're going to use what's called a dilution formula. We have the first molarity times the first volume, and that will be equal to the second molarity times the second volume. This will allow us to create any concentration that we want. A lot of times the chemical suppliers will sell all different kinds of concentrations of their chemical, but when I purchase chemicals for our lab, I always purchase the most concentrated form I can get my hands on because I can dilute it down to whatever concentration I want. If I purchase less concentrated chemicals from the chemical supplier, I'm paying for a lot of extra water that I could add myself for free. So this formula right here is a real money saver. Let's do a practice question. What concentration of sodium hydroxide would be achieved by adding 2 liters of water to 1.5 liters of a 6 molar sodium hydroxide stock solution? Okay, so the first thing we're going to do is write down our dilution formula. Now we need to decide what of these numbers represents which of these variables. Okay, so they said right here achieved. That means that it's going to happen after something else. So they're asking what concentration of sodium hydroxide would be achieved by adding this amount, this volume of water, to this volume and molarity right here. So this must be the original molarity, and this must be the original volume, and this must be the second volume, and so I'm trying to figure out what the second concentration or the second molarity is going to be. So I'm trying to find out what M2 is. So let's resolve this equation here for the second molarity. Alright, and now all we have to do is plug in our given information. And we come up with a 4.5 molar solution of sodium hydroxide. So we have diluted it from 6 molar to 4.5 molar. Okay, let's do another question. A chemistry teacher is preparing for a lab for his chemistry students and has calculated that he needs 55 milliliters of a 6 molar stock solution of hydrochloric acid. He has a 12 molar solution of HCl in the chemical supply room. What volume in milliliters of the stock solution should he use to create the desired HCl solution? And what volume of distilled water would have to be used to dilute the 12 molar HCl solution to the correct molarity? Alright, let's answer question A first. We're going to need to write down our dilution formula. Now we need to decide what we are being asked to solve for. It says what volume in milliliters of the stock solution. Stock solution means that that's what we already have on hand. It's the thing that we're starting with. Since we're starting with it, it must be on this side. So they are asking for V1, the original volume. So we need to resolve this equation for V1. Now all we need to do is plug in our given information. Okay, so when we do that, we come up with 27.5 milliliters of HCl, and that is our answer to letter A. Now, of course, we need to adjust for significant digits. It looks like 2 is the fewest number of sig figs, so we need to bump that up to 28 milliliters. Alright, now for part B. What volume of distilled water would have to be used to dilute the 12 molar HCl solution to the correct molarity? Okay, so right here we found out what volume of HCl, the actual acid, is that we need to use, but we don't know how much water to add to this much hydrochloric acid. Here's how you do it. This 55 milliliters here is the entire amount of solution that you're going to end up with at the end. That's what this chemistry teacher is going to use for his lab. Now, inside of that 55 milliliters is going to be acid and water. We just calculated how much acid is going to be in there. We don't know how much water is going to be in there, but we know that both of them are going to have to add up to be 55 milliliters. So we're going to do 55 minus the 27.5, and that'll tell us how much water we have to add. So we have 55 milliliters of the solution minus 27.5 milliliters of the concentrated 12 molar hydrochloric acid, and that's going to give us 27.5 milliliters of our distilled water. Notice how we got the 27.5 here and the 27.5 up here. The reason is because we are exactly halving the concentration of our stock solution. We went from 12 to 6, so we went down by 1/2. That means that half is going to be acid and half of it's going to be water. If I had chosen a different concentration for our lab, or if the stock solution had a different concentration that wasn't exactly half, then that means these numbers would be different. But I chose this so that it was easy for us to see the problem here. So you're going to have 28 milliliters of the acid, and you're going to have 27.5 milliliters of the water. Remember, our significant digit rules are different when we do addition subtraction. In that case, we answer with the fewest number of decimal places. This one goes out to the tenths place, this one goes out to the hundredths. That means our answer needs to go out to the tenths place. So this actually is the final answer for part B, and this one's the final answer for part A. Now, in an actual lab situation, if you were really doing this, you would want to do the 27.5 for Alright, the next thing that we're going to talk about are the ions that dissolve into an aqueous solution. And we're going to talk about what are called colligative properties. The first thing we're going to do, though, is talk about those solutions. We're going to memorize a set of rules. They're called the solubility rules. And they help us decide which compounds are going to completely dissolve and which ones will only partly dissolve. Remember, we have strong electrolytes, and we have weak electrolytes, and we have non-electrolytes. These set of rules are going to help us determine which molecules fit into which of those three categories. Alright, so strong acids are going to completely dissociate into their ions. So that's what we're going to consider to be a strong electrolyte. The following acids are strong. So hydrochloric acid, hydrobromic acid, and hydroiodic acid are all strong. And then any acids that have 2 or more oxygens than hydrogens are strong acids. Any organic acids are weak. Remember, organic means carbon containing. So this one here would be something like sulfuric acid. So here we have 4 oxygens and 2 hydrogens. That means we have at least 2 more oxygens than we do hydrogens. So this is a strong acid. Then we have strong bases. Those would be hydroxides of group 1A. This is the first column on your periodic table. So any element that you form a hydroxide with that comes from group 1A is going to be a strong base. So for example, sodium hydroxide. Okay, the sodium comes from group 1A, and then we've made a hydroxide of it. So this is a strong base. Okay, and then calcium, strontium, and barium hydroxide are all strong bases as well. Those are in the second column, and they are right on top of each other. You can see those right here. Okay, calcium, strontium, and barium. So all of these can form strong bases, and calcium, strontium, and barium hydroxides can form strong bases. Alright, so that's the acids and the bases rules, which are pretty easy, and then we have the salt rules. Now these can get a little bit more complex. If any of the following things are in a compound, then the compound will be soluble, unless they're paired up with these things over here. So if a salt has something from group 1A, if it's got the nitrate ion, ammonium ion, chlorite, chlorate, acetate, or phosphate ion attached to it, it's always soluble with no exceptions. Here's some examples. So here we have NaCl. Sodium is from group 1A, so that automatically means this is soluble. It's going to dissolve in water to produce the ions Na+1 and Cl-1. That's what a soluble salt does. It will dissolve in water and produce the ions. Okay, right here it says that the ionic compounds, the metal and the nonmetal, will separate from each other. Here, nitrate, so here's the nitrate ion. That means that this salt must be soluble. So you get the magnesium +2 ions, and you get the nitrate -1 ions. This has ammonium in it, so it would separate and give us the ammonium +1 and the chlorine -1 ions. This has the chlorite ion in it, so those two would separate. This one has the chlorate nonmetal, so those two would separate. This has the acetate ion in it, so those would separate. And this has the phosphate ion in it, so those two would separate. Okay, next on the list. If they have chlorine, bromine, or iodine as the nonmetal or the anion, then they will always be soluble unless you pair them up with silver, lead, or mercury 2. So here's an example of that. If we did lithium chloride, it would be soluble because anything that's attached to chlorine is soluble unless it's one of those three. Plus lithium is in group 1A, so that falls back to this rule here. This one, however, is not soluble because chlorine is attached to a lead 2 cation, so that's not soluble, which means it won't dissolve in water. It'll be like a little powder or something that just sinks to the bottom and you won't be able to get it to dissolve, like sand in the ocean doesn't dissolve. And then finally, anything that's attached to a sulfate ion will be soluble unless it's one of these three here or those three there. Now this one I just kind of think that one's pretty easy because it's the three from right up here plus the calcium, strontium, barium was what we saw in the bases. So if you just remember both of those exceptions, then it's not really hard to memorize. So let's give an example. Alright, so iron 2 sulfate is soluble, but silver sulfate is not soluble. So pretty easy. You're going to need to memorize the strong acid rule, the strong base rule, and your soluble salts rules. That's this whole table with the exceptions. Now, if it doesn't fit any of the rules that we just discussed, then you're going to assume that it's insoluble, meaning it will not dissolve in water. It's not going to break up into the ions, and therefore it is a non-electrolyte, or sometimes it's a weak electrolyte. Now, it's not going to be always correct to make that assumption, but for the purposes of this class, it will be. All right. A few more things we need to remember. Gases, pure liquids, and solids are non-electrolytes, meaning they will not break apart into ions. So pure liquid would be something like water. Water is a pure liquid. It is not going to separate into ions. Hydrochloric acid, when it's not dissolved in water, meaning it's not aqueous, it's a gas, or it's the liquid form of hydrochloric acid, that will not separate into ions. It's a pure liquid. But once you dissolve it in water, then it will go ahead and separate. And then these right here, remember when we did our predicting reactions, we had a couple of acids that I told you to watch out for because they'll decompose into secondary products. Remember those. If you have carbonic acid, it's going to decompose into a pure liquid, water, and a gas. So you don't really get any ions from that, so it is not going to be a strong acid. Same thing here, if we have a gas, that's going to change that into a liquid, and that's a gas. Ammonium hydroxide decomposes into these products, and water is a weak electrolyte. So you need to remember all of those things and make sure that you can apply them for the section that's going to come up in just a minute. Again, reviewing strong electrolyte, it's anything that can conduct electricity when dissolved in water, and a weak electrolyte will only weakly conduct electricity when dissolved in water. Okay, so now we're going to talk about what we call net ionic equations. And that is when we write an equation that only shows the ions that participate in a chemical reaction. We need some vocabulary words in order to be able to write our net ionic equations. The first thing we're going to talk about is dissociation, and that is the separation of ions that occur when an ionic compound, such as a salt, or our strong acids and strong bases, dissolve in water. Now, some of the ions will actually participate in a reaction with each other, and other ions are called spectator ions because they just sit and watch. They do not participate in the actual reaction, and so we actually can just cancel those out. So let's actually learn how to write a net ionic equation. The first thing you're going to do is write the molecular equation. That's what you know how to do right now, is to take the compound, predict the products, and balance it. That's called a molecular equation. The next thing you're going to do is write all of the strong electrolytes as ions, meaning you're going to separate them into their aqueous ions for the whole reaction. And you're going to use your solubility rules to do that. Then you're going to eliminate all of the spectator ions, and then you'll write a balanced net ionic equation with the remaining ions. The best way to do this is to just dive in and do some practice, okay? So let's look at this first example question here. Consider the reaction between solutions, and when they say solutions, that means that these things have been dissolved in water. If these were pure substances, then it wouldn't work. We need it to be a solution. Okay, so a solution of sodium chloride and lead 2 nitrate. Alright, so here we have our sodium chloride and we have our lead 2 nitrate. Now these should say aqueous next to them because it's a solution, meaning they've been dissolved in water. And then we predict the products. This is a double displacement reaction. So the sodium is going to hook up with the nitrate, which we see here, and the lead is going to hook up with the chloride, which we see here. Now, since that 2 is right there, it means that this was a lead 2 ion, so that's why there's a 2 here. And then we know that sodium's +1 and nitrate is all the rest, so it's -1. Alright, so we've done all of our crisscrossing, reducing, and we've checked all of our charges, so we're good. Step 2 is to write all of the strong electrolytes as ions using our solubility rules. So if we go back and we check our solubility rules, remember that all salts that have a group 1A metal in them are soluble. That means this is going to break down into sodium ions and chlorine ions. Anything that has nitrate ion in it is also soluble with no exceptions. So we'll break it down into the lead 2 ion and the nitrate ion. Then we come over here. Anything that's attached to a chlorine ion is soluble unless it's silver, lead, or mercury. And this happens to be attached to lead. So this will not break apart in water. This will stay soluble. So this is a solid. And then here, there's a group 1A and nitrate. So this is like super soluble. It will definitely break apart into sodium and nitrate ions. So let's write all that out. Okay, so we have our sodium and our chlorine broken apart, just like we predicted. We have our lead 2 and our nitrate broken apart, just like we predicted. This stays together because it's not soluble, so it will not break apart. And then we have the sodium and the nitrate, and they have broken apart. Then we're going to eliminate the spectator ions. Spectator ions are ions that appear on both sides of the reaction arrow. So here we have sodium and here we have sodium. We would cancel those out. Here we have nitrate and here we have nitrate. We would cancel those out. Alright, that means that we have the lead ions and the chlorine ions left on this side and then the lead 2 chloride over here. So now we're going to write the balanced net ionic equation out of whatever's left. Okay, so we have 2 chlorines over here, so we had to multiply by 2 on this side, and 1 lead over here, so we left it as 1. So this is the balanced net ionic equation, where we have our ions over on this side, and then our solid product over here. Now, I've been bad, and in class, you know, I'll do better, but you really have to put what state these are in order to get this correct. So we really need to put in here that that's a solid and that these are aqueous, meaning that they have been dissolved in water. Otherwise, we will not get this question correct. Okay, so we have ions over here and then a solid product over here because that's insoluble. Alright, let's do another one. Write the net ionic equations for the following and make sure you balance them. We have a solution of silver nitrate and hydrochloric acid, and they're mixed together. So the first thing we want to do is predict the products of that reaction. Okay, so we have predicted our reaction, and now we need to use our solubility rules to decide which things are going to disassociate and which things are going to stay together. So I see that we have nitrate ion here. That means that this is always soluble. It'll break down. I see that we have hydrochloric acid, and according to our hydrochloric acid, our acid rules, this is a strong acid. Here we have chlorine, which is always soluble unless it's paired with silver, lead, or mercury too. So this one will stick together. And then another acid. Acids that have two or more oxygens than hydrogens are strong, so this should separate as well. Let's write that. Alright, so we've split apart all of our soluble ions. Notice that if they were soluble, if they disassociated, then they're aqueous. Okay? If they didn't, then they're solid. Now we need to cross out our spectator ions. So we are going to mark out things that are still present on both sides of the reaction arrow. So it looks like the hydrogen ions are both there and the nitrate ions are both still there. So we're going to get rid of those. That means that we're left with the silver ions and the chloride ions, and so we'll make the silver chloride. So now we're going to write that. Alright, and so here we have our balanced net ionic equation. All of the coefficients are 1, and we have all of our states listed. Oops, we need to put aqueous here. Okay, so let's try another one. We have hydrochloric acid is poured over sodium carbonate crystals, and sulfuric acid is added to barium hydroxide. See if you can go through, write the molecular equation first, then do the net ionic equation, then cancel out all your spectators and do the final balanced net ionic equation for both of these, and we'll come back and see what you got in just a second. Okay, here's what I've come up with. Let's run through this really quickly. This is a strong acid, so it breaks down. This has a group 1 metal in it, so it breaks down. That's a pure liquid. The reason for that is because the hydrogen would pair up with the carbonate ion and become carbonic acid, but then that breaks down into water and carbon dioxide gas, and so those are pure substances, so they don't break down into ions. And then the sodium pairs up with the chlorine, so there's another group 1A, so those break down. Then we cross out our spectator ions, and then we have our hydrogen plus the carbonate ion gives us the water and the carbon dioxide, and then we have to balance it. So we have 2 hydrogens over here, we need 2 over here, 3 oxygens, there's 1, 2, 3, and then 1 carbon on each side. So that one's balanced. Then this one, this has 2 or more oxygens and hydrogens, so it's strong, which means it breaks down. And then hydroxides of group 1A metals and calcium, strontium, and barium will break down. And then everything that's paired up with sulfate is soluble unless it's silver, lead, mercury, or calcium, strontium, barium. So that means that does not break down, it stays solid. And then that's a pure liquid, so it will not break down. That means that we don't have any spectator ions to cross out, so this is the net ionic equation, and it's also balanced. We have HOH, which is H2O, and then we have barium and sulfate, so that comes together there. So hopefully you ended up with the same thing as I did.